Potential to utilize wood biomass heat in poultry barns, December 5, 2017. Presented by Steve Knobeloch and Tom Wilson of Wilson Engineering Services. Minnesota State Wood Energy Team presents a webinar on opportunities for heating poultry barns with wood. This webinar and study are made possible through a grant from the U.S. Forest Service to promote rural economic development, prevent wildfire by decreasing hazardous fuels, and increase renewable energy. The webinar covers why a farm or any facility should look at biomass, what are the basics for biomass heating systems, different appliances and installations, fuel specifications, and how a biomass system applies to a poultry farm servicing multiple barns. The presentation ends with a look at the economics of owning and operating a biomass system and at other benefits a biomass system might provide to a poultry farm. Wilson Engineering Services, based out of Pennsylvania, was hired by the grant team to conduct a feasibility assessment for heating multiple poultry barns using a single biomass, wood, heating system. The results of the study are being presented by Wilson Engineering Services project manager of the study, Steve Knobeloch. Joining him as a panelist is Tom Wilson, president of Wilson Engineering Services. We pick up the webinar in progress with Steve Knobeloch explaining that a poultry farm or any facility should consider biomass to lower energy costs as fossil fuels increase in cost again.
But prices have been ticking upwards recently, and I think we're back over $1 a gallon. It was just a few years ago here in Minnesota where a higher energy price environment combined with some supply constraints and really a cold winter spiked propane prices pretty high. I think we reached over $4 a gallon for a brief period of time. The wood, residual, and fuel market, on the other hand, has been a lot more stable in Minnesota, and actually with the anticipated closing of biomass power plant in Benson, wood prices may slightly be depressed moving forward as new wood markets are explored. So as you can see on the table here, at propane prices of $1.25 per gallon, wood energy could be expected to be half. The heating cost can be expected to be half the price or less. So that's usually the main driver for why you will consider biomass energy is lower energy costs. Sites that have good potential for a biomass project are sites with high heating demands and or high fuel costs. These sites would provide enough in fuel savings to overcome the upfront capital costs of a biomass system. A readily available supply of wood is needed for obvious reasons. It's best if you can have multiple suppliers available so as not to be completely beholden to a single supplier. Access for delivery of wood is of course needed to manage wood handling on site, and some level of available manpower is also needed to perform routine checks on the boiler as it's running and other tasks depending on the level of automation of your system. Available space on site is of course necessary. Biomass boilers are physically larger than comparably sized fossil fuel boilers, and because we're dealing with a solid fuel, more space is going to be needed for storage and handling. A poultry farm meets those criteria very well, especially one without access to natural gas. Energy costs are usually one of the top two expenses. A challenge that has to be overcome for a poultry barn system is the ability to integrate a biomass system into the existing heating systems Conventional heating systems usually use an array of direct fired gas equipment, which would have to be replaced if a biomass system were to be installed. So biomass systems are usually designed with a specific wood fuel in mind. Different wood fuels are suitable for different heating applications. Wood boilers that would utilize wood chips can accept a variety of moisture contents. Green chip boilers can accept a range from 10% to up to 50%, which would be green chips. Those boilers are physically larger, usually with a more robust handling system. Dry chip boilers, on the other hand, can be purchased as package-style boilers, which provide lower upfront capital costs. But these boilers are typically smaller and will require wood chips of a lower moisture content, usually 30 and under, and require a reasonable amount of screening of oversized pieces. With the size and scale of most poultry farms, I think a wood chip boiler, and specifically a dry wood chip boiler, is a nice fit. Wood pellet boilers are another option. They're lower in capital costs, upfront costs, but wood pellets are a higher cost fuel and don't necessarily offer as much, or at current prices offer very little in the way of energy savings. Boilers that'll burn cordwood are also available. These systems are typically very labor intensive, as staging of wood and loading of the boiler is a very manual process. These systems might be beneficial for some sites if access to low or no cost cordwood is available, or where labor costs are very, very minimal or free, so to speak. So modern biomass boiler systems will use a staged combustion process in which the wood is first dried of any remaining moisture content, and then gasified, and then the wood gases are completely combusted. This process is a very efficient process and essentially converts all energy locked in the wood to heat. Combustion air in these systems are usually controlled by variable speed drives on the fans, and maintain proper air to fuel mixtures, which maintain good efficiency and low emissions of the systems. With the installation of just about any biomass boiler, hot water boiler at least, thermal storage is always recommended, especially if it's going to be used for space heating where the heating demand will fluctuate. Thermal storage is essentially storing of heat in the form of hot water at elevated temperatures, usually above that of which it will be used. It's a very, very key, I want to stress that, it's a very key component for systems in which heating demands fluctuate considerably, like poultry barns. Thermal storage provides an immediate response to fluctuating demand, while provides a more uniform load on the boiler unit itself, which improves efficiency. Thermal storage also provides an outlet for heat during low demand periods. When heating demands are low or non-existent, the residual heat in the boiler has somewhere to go. The storage of heat above distribution temperatures kind of maximizes the heat storage capacity of the thermal storage tank and allows the allows the system to meet short-term peak demands above the rated capacity of the boiler. You get more bang for your buck. Wood storage and handling. The most common delivery method for wood is going to be walking floor trailer, which are very, very common in the poultry industry for delivering animal bedding and things like that. Bulk storage of wood chips, your storage bunker, so to speak, should be sized such that it can accept a full delivery of wood from a walking floor trailer, from a full 50-foot trailer, with additional capacity available to keep the system running while a delivery is scheduled. Trucking is a very significant cost to the delivered price of wood, and the ability to accept full loads, it's crucial in getting competitive pricing. Handling systems can range from small bay bins, which would be loaded by a tractor or a front end loader from a bulk storage area, up to fully automated storage systems which use a live floor or some method of reclaim to transfer wood from the bulk storage area to the boiler. Fully automated systems, of course, do add capital costs to the project. So some potential fuel suppliers for a dry chip, which would be suitable for most size poultry farms, are, typically are going to be forest product industries like sawmills and that sort of thing. Another great supplier in this particular part of the country or in Minnesota in general are bedding suppliers. They make a lot of sense. The suppliers already have the feedstocks, the drying equipment, screening equipment, delivery vehicles needed to provide fuel chip, and specifically those that provide shavings, very minimal changes are needed to provide a suitable fuel chip. The wood chip specs for a dry chip boiler typically need to be screened to 1.25 inches minus or less than 1.25 inches. Moisture content should be under 30%. Lower moisture contents will provide more heat in the sense that you don't have to drive off the water, so they're more efficient systems. Hardwood and softwood are both acceptable fuels. The primary difference between the two in terms, as it relates to boiler systems, is softwood is less dense, so it's going to take a larger volume, on the order of 10% more, to provide the same energy input. On a per ton basis, the energy contents are similar between hardwood and softwood. So the overall heating demands for a poultry barn, they're a function of a few different heating factors. Obviously, heat loss through the building walls is a big one. These losses can be minimized to some degree through good insulation. Ventilation loads, which is the energy required to heat fresh air brought into the barn, is a very significant heating load, and it's often a trade-off between ventilating the space for moisture control versus keeping temperatures up and minimizing energy costs. Latent heat loads are due to the evaporation of water from the bedding or litter. This has a cooling effect on the bedding, and that's where the birds live. So you know it's essential to keep the bedding at an appropriate temperature for bird comfort. And then finally, the birds themselves provide a significant amount, as they age, significant amount of heat gain to the environment. It's not a very significant factor during the early weeks of their life and during brooding, but when birds are older, the heat gain plays a significant role. So the differences between a brooder barn or finishing a grow-out barn as it pertains to the heating demands, the two different types of barns are operated quite differently, so heating demands will be different. Brooder barns start out at a much higher temperature, as high as 90 degrees, but because birds are smaller and will consume less water, ventilation rates may be kept much lower, as moisture control is not as big of an issue. The barn itself is usually much smaller, as the young birds need less space. You know, due to these factors, heating demands for brooder barns tend to be relatively stable. As with the finishing barns, a high amount of ventilation is required, and fluctuating outdoor air temperatures can really cause fluctuating heating demands within the barn. Conventional turkey barn, poultry barn heating systems are either radiant heaters or forced air furnaces. They're typically all direct fired units, which means 100% of the heat is emitted into the environment. There are no flue gas losses, nothing goes out a stack anywhere, which is very efficient. On the other hand, you're introducing other combustion byproducts into the barn atmosphere. These conventional systems, gas-fired units, are chosen because the equipment costs are very cheap. Operation is relatively simple. It's a hydronic heating equipment, on the other hand, which is what would be served by a hot water boiler. It requires a heating source, such as a boiler, and which could be either propane or fossil fuel or biomass. But hot water is circulated throughout the barn for heating and requires a heat emitter to transfer that heat from the hot water to the barn. Fan coil units are the most common, and they are essentially just a hot water coil with a fan blowing air over it to heat the barn. There are models of fan coil units specifically designed for poultry barns, and design considerations for poultry farms really are mostly due to dust. That's the main design consideration. They're designed to be robust to handle several cleanings of dust off the tubes and the fan blades. In-floor heating systems are another form of hydronic heating, in which hot water is piped through the slab. These systems aren't necessarily common for poultry barns, though installation costs tend to be very high, and an additional heating system is going to be required anyway, because you can't get all your heat from the floor. The bedding provides some insulating factor, and you can't have floor temperatures elevated such that it would provide an uncomfortable environment for the birds. So a typical layout might look something like this. It shows four poultry barns and a central boiler plant. And looking at a layout for a biomass boiler system, with a central plant serving a district system, hot water is circulated from the central heating plant to the barns through insulated underground piping. And then once it gets into the barn, it can be ran overhead to each fan coil unit or other heat emitter. Boiler plant location is key in the layout of these systems to minimize piping runs, which can make up a significant cost to the installation of such a system. And then consideration must also be given to delivery vehicle access. How is the wood going to be delivered to the boiler plant? This slide shows a basic boiler connection diagram. As you see here, the biomass boiler is being used to heat a thermal storage tank, and then from the thermal storage tank, hot water is distributed to the distribution system. A thermal storage tank will utilize a three-way mixing valve, blend higher temperature water stored in the tank with cooler return water to meet the desired temperature for the distribution. For periods in which demand might exceed the biomass system capacity, it's always recommended to have a backup boiler, and a boiler for peak demands to provide additional heat. Or the alternative is to use multiple biomass boilers that can be staged. A peaking boiler, in this case that shows a propane boiler, would be operated to provide heat to the system should the biomass system not be able to maintain the set point temperature. A propane boiler backup also provides redundancy should the biomass boiler system be offline for any reason. A quick note on boiler sizing. Biomass systems generally should not be sized to meet peak loads, at least with a single unit, but rather to cover as much load as possible. I mean, the primary goal is displacing as much propane and higher fuel cost energy. So they should be sized to offset as much load as possible. These systems typically have a turn down of 4:1 or down to 25% of the rated capacity, and performance can suffer at the lower firing rates because of the relatively large thermal mass of the unit and longer combustion times for solid fuels, relative to gas. Response is slower. A properly sized system would displace 80 to 90% of existing fuel use. 100% fuel use can be offset through the use of multiple boilers as well, multiple biomass boilers. So the capital costs for installing a biomass system such as we've discussed so far are made up of a handful of items. The type and size of boiler is going to play a large role. The larger boilers will increase cost, which is another reason for avoiding oversizing boilers. And then optional features like auto ignition, auto cleaning, auto blowing out of the boiler tubes, auto de-ashing also can add cost to the system. Thermal storage tanks can be a significant cost, particularly if it's a pressure-rated tank. Heat distribution systems for a district system, for a system that serves multiple buildings, is going to be very significant in terms of underground piping, pumping costs, all valves and all the heat emitters that are required. A fuel storage and handling system is needed, and the level, to the degree that the system's automated, is going to increase costs of a system. It's most likely, especially for a poultry farm, that a new building is going to have to be constructed to house the boiler system and the wood storage, which is a significant cost, and then an access for delivery vehicles must also be considered. So operating costs, in addition to the fuel costs, there are other operating costs of owning and operating a biomass system. The daily operation of a boiler will include routine checks just to ensure everything is operating properly, occasional ash emptying, which can be, depending on what system you can choose, could be as much as every other day or once a week. And then loading of a day bin, using a front end loader. These duties might be expected to take 30 minutes to an hour each day. The feed systems will also require occasional inspection to ensure they're operating properly. There may be an occasional fuel jam that will have to be cleared. The boiler combustion chamber itself, it's recommended that it be cleaned on a semi-annual or annual basis to remove ash buildup and any clinkers in the combustion chamber. And then it's recommended that you have the system serviced annually or every so often by a service technician. Something that's often overlooked in the analysis of a biomass system is the electric energy that is required. There are pumps, there are fan motors, there's fuel feed motors that all take electric energy, and that'll add cost to operating the system. Now, one of the benefits of system, a perk in the state of Minnesota for these systems is its Biomass Thermal Incentive Program. This program pays facility owners $5 per million BTU of thermal production output using biomass fuel, and it pays for every million BTU of output with quarters where over 250 million BTUs of production has been achieved, which is comparable to about 2,800 gallons of propane. So for a poultry farm, it's probably every quarter of the year. This program will pay owners for 10 years after the startup of your biomass system. So if you started up next year, it's going to be 10 years starting next year. They do require that the biomass feedstock be sourced from the state of Minnesota. And there's some leeway given if you're on the border of the state, but they want in-state resources used. So what effect does that have on wood fuel costs? It's significant. This brings down the cost of dry chips to about $2 per million BTU of output, which compared with propane at $1.25, you know, it's over $13. So it's significantly cheaper when you include incentives that Minnesota has for biomass energy. So let's look at a theoretical example poultry farm as an example. This farm described here uses about 50,000 gallons of propane a year for heating its barns, and this would be in the ballpark for a farm with 3 or 4 turkey barns. Assuming an energy cost of $1.25 for propane and $80 a ton for wood, it might look something like this. Fuel costs, existing fuel costs, $62,000 with a propane system, and then about $35,000 for a wood system. That would provide savings of about $27,000 per year, which at current prices, payback on this type of system, you know, is still over 30 years. However, that's heavily dependent on the projected energy costs. For this example shown, would achieve a 10-year payback with propane in the area of $2.20 a gallon. There are some economies of scale achieved should a system be installed on a larger facility, which will improve payback, offset more propane gas, and provide more energy savings. There are many of the capital costs of a biomass system are fixed costs or would only increase slightly with the installation at a larger site. Building costs are one that wouldn't change. Any site work for access is going to remain unchanged for a larger scale as it would for a smaller scale project. And then boiler costs. With the diversity of load of multiple houses, boiler, with doubling the number of houses doesn't double the load on the boiler necessarily, and boiler costs might only increase incrementally. Other costs will increase though with the increase in scale, namely piping costs and heat distribution costs. So a biomass system would also provide other improvements to the turkey barn environment. As we mentioned earlier, conventional gas equipment are all direct fired. As all of the heat and all of the combustion byproducts are emitted into the barn. The primary two byproducts which will affect bird health and growth and performance are water vapor and carbon dioxide. Increased water vapor in the air raises the barn humidity and then makes it more difficult to keep the bedding dry, which leads to ammonia formation, which can adversely affect bird health and human health. High firing rates combined with low ventilation, which is a condition that's present in the early weeks of a young bird's life in the brooding barn, can increase CO2 levels such that some amount of oxygen is displaced, and this will adversely affect bird growth, leads to lethargy and poor feed conversion. The risk of a malfunctioning gas equipment is also removed with an indirect heating system, removing the risk that carbon monoxide could be released into the environment. Another advantage that is not often discussed, but I know is a sensitive topic in Minnesota, is fire hazards. The indirect systems can be located away from the poultry barn, which removes the risk of a fire in the poultry barn itself. So this is a chart of water vapor output from a conventional heating system in terms of gallons per day versus its average firing rate. For cold winter conditions, firing rates may approach 1 million BTUs an hour for a typical poultry barn, and in these conditions you're adding over 200 gallons of water per day to the environment, which either increases the humidity of the barn or requires significantly more fan energy and ventilation to remove that moisture. The improvements to barn environment and bird health primarily are less ammonia formation. This would be expected to improve bird performance in terms of reduced mortality, improved feed conversion, shorter grow-out period. In addition, less fan energy is required to ventilate the barn, and lower ventilation rates may be used, which further reduces the heating demand for the system. Some of these factors are difficult to quantify in terms of an economic analysis, but they're provided by a biomass system nonetheless. So some other general benefits for using wood energy in the state of Minnesota are your dollars are going to be kept within the local economy. It's going to help the trucker or the logger as opposed to being sent out of state or even out of country. Having biomass heating equipment and propane equipment on site gives you a diversification in your fuel options and can help protect your operating costs from volatility in the oil or gas market. Carbon footprint of your facility is going to be reduced with biomass heating. It's a renewable energy form, renewable, sustainable. And then utilizing low-value residual wood strengthens the market for that wood, which provides an outlet for forest management practices, helps combat soil erosion, wildfire, that sort of thing. So those are the benefits of a biomass system. And with that, I'll open up the panel and we'll take any questions anyone may have. I'll turn it over back to you, Kristen.
Yeah, thanks, Steve, for that presentation. There is some questions and by Greg Langmo. I apologize if I didn't pronounce the last name correctly, in the Q&A box, and we will address those. If anyone else has some questions they would like to ask, please put those in the Q&A box, and we will talk about them. So, Steve, I believe you can see the Q&A as well. I can read the questions that Greg has and comments that Greg has as well. The first one is, the cost of wood in an earlier slide looks very high, 35% wood at 3% ash. with all in cost of $30 a ton calculates to less than $3 per MMBTU, not over $7. How comfortable are you with your numbers? I believe that was a slide more towards the beginning of the presentation, Steve, if you want to address that. And then there's some other questions related to the fuel pricing that you utilized in the study, if you can speak to that.
So, yeah, on a per million BTU basis, it's including the seasonal efficiency of the boiler. So this is in terms of heat output, not heat input, which is why it's over, why it's not $3, it's $5. I don't know, Tom, if you have anything to add.
No, I think that covers the green chips at 65% efficiency is relatively conservative, but it's the data that we see when we do a lot of work analyzing the efficiencies of these boilers. Green chips, 35%. Typically, it's hard to get a whole lot above 65% on a seasonal basis. That's why it's 538. Again, that's a little conservative, but it's pretty close.
Okay, yeah, and Greg makes a comment that wood consistently under 30%. I'm assuming moisture is hard to find. Equipment should be able to burn a wide variety of moisture and particle size to manage costs, fuel procurement.
Steve, you want me to take that one?
Sure.
Well, if you look at the cost of installations, most of these systems are not real big. They're in the, 2 million BTU an hour or under generally. Steve, I don't know in the test case, what was the size of the furnace that we looked at?
I believe we looked at
right?
1.5 million or 1.7 million.
Yeah, and these smaller biomass systems, you're absolutely right. If you make a more robust system, you can handle anything. But the problem with that is the capital cost on these smaller systems tends to get really a lot higher if you start adding sorting, and the smaller units then have to be more robust. And so typically the market, especially since you've got bedding producers there that already have drying systems in Minnesota, and they already have agreements or contracts with these farms, they're able to easily meet those requirements of 30% and under, and they already have a stream, whether it's log staged or handling residuals from sawmills. Larger systems, we really design larger systems to be robust and handle all types of materials. In fact, we think that's a key, so that the boiler owner can be opportunistic. But in these smaller systems, you start adding so much capital cost, justify the savings or the opportunity cost for the non-specialized fuel, you just can't get it paid back.
Steve, I think if you can see the Q&A questions as they come in, if you want to just work down the list and address them, that would be most efficient.
So in our example case, we looked at a dry chip boiler to handle 30% and under wood chips, and then it includes piping costs to barns, and then the heating equipment to provide heat to the heat of the barns. So that was, and that's a building cost. That's all in cost for that type of system. It's a 1.7 million BTU an hour boiler system, suitable for dry chips. A general rule of thumb for thermal storage sizing relative to boilers that we've seen is 100 gallons of thermal storage for every 100 1,000 BTUs per hour of output, and so that was the boiler size and thermal storage quoted in that scenario.
Steve, there are several more questions here on the cost. The $80 a ton was a direct quote we got from a supplier who was processing wood pallets and other items, and we used that in the study. It's a little bit, it's conservative. You know, we would expect you to be able to get the dried chips maybe closer to 60 a ton, but it doesn't radically change the economics. What radically changes the economics is the price of propane. And there's another question in here about fuel quality, ash or litter can cause slagging. That's absolutely correct. Generally, the wood chip boilers and the dry wood chip boilers do not slag. Where we see slagging is when you take a wood chip boiler and you try to burn completely dry pellets in it, where the temperatures get too hot and you get above the melting point of the ash. And the other one is litter is definitely takes a specialized piece of equipment if you want to burn poultry litter. Literally some kind of flue gas recirculation or some method to decrease the combustion zone temperatures required, or you definitely get slagging in those environments.
There's another question: how much would you size a biomass boiler according to the peak heating load, 50%, 80%, and so on? It's really going to depend on the load, how the load duration throughout the year. You're going to size it to cover as much load as possible. So it really depends on what that load curve looks like throughout the year. 80% is probably I would say typical, but again, it really varies based on the individual facility, and the name of the game is just offsetting as much propane as possible. So.
And the load curves for poultry buildings look a little different than they do for typical heating, and the reason is you've got that latent heat and you've got the ventilation requirement. So again, as Steve says, without modeling it, it's tough to use a rule of thumb. I know in heating a building, especially in a cold climate like Minnesota, you might say that typical sizing of a biomass system to heat a building would be maybe in the 50% range. But again, that's a rule of thumb, and rule of thumbs not really. That's not why you pay the engineer to get the rule of thumb.
Another question for poultry: can you stagger the barns by 2 to 3 weeks, or do they operate in an all-in, all-out scenario? I assume that means the operating schedule of the week of the barns, which is absolutely the practice of most poultry farms anyway, so that you don't have just for their own operating conditions. So yes, they are staggered, and the heating demand is a bit diversified in that sense.
And typically they're staggered by the brooding barn schedule. Brooding takes usually about 6 weeks with 1 week clean out in between. I think that turkey overall growing schedule, they go from 0 up to 22 to 23 weeks. Depends on the bird and the rate of growth, but that's pretty typical. So one brooder barn would typically serve maybe 3 growing barns over that 21-week cycle. So they definitely are staggered the loads, which is an advantage for sizing of a biomass system. The question about ash, ash is certainly a soil amendment. It can be used and put back on the soil, mixed into your work great as compost, helps compost in the dead bird pile or whatever you're doing with the waste or the manure that's coming out, and certainly can be land applied. The volume is really small, though, if you're looking at the economic benefits. Typically, we see less than 0.5% ash coming back on a reasonably clean wood chip that's actually collected. So it's not a very big volume, and that's on a dry matter basis. So it's a pretty small overall volume. In fact, everybody that puts in an automated wood system with fairly clean wood is usually shocked at the limited amount of ash that comes out.
Looks like there was one other question, gentlemen, and I can take this one. Are there any poultry barns in Minnesota using biomass wood heat currently, similar to the systems presented? To my knowledge, there is not. There is some producers who are using wood biomass directly connected to a barn. This system looked at heating multiple barns, so that would be the difference. There are some growers who are utilizing wood heat for barns in the state, but not, I don't believe there are any that are utilizing this particular system heating multiple barns at one time currently. Looks like there's a few other questions, gentlemen. What is the life expectancy of a boiler and of the piping?
Steve, you want to take that?
Sure. The life expectancy of the boiler unit itself, we expect it to be 25 years, as is typical with some conventional fossil fuel boilers of the same size. Tom, do you want to speak to the piping?
Yeah, I think that's, I don't know what the horizon is, 50 years or more when it's in the ground, and even the above ground piping. And Steve and I actually make a living working on all these boilers that are a lot older than 25 years. So there are, 25 years I think is a reasonable expectancy without any major reworks or overhauls other than ordinary maintenance of a system. We see all kinds of analysis, 30 years, 50 years, but you get out much beyond 25 years, and that's generational. So I think it's realistic to extend it beyond that. But these are robust systems; they last a long time. If you buy a good quality boiler and the pipe, we haven't seen what the life is because we've got these installations that are, I don't know, 50 years is probably realistic for piping before it needs to be replaced, but you'll start replacing pumps and components way before that. But 25 years is very conservative in life cycle analysis for all the components.
There was a question, what lower heating value, higher heating value are you using for LP? And we used a figure of 91,300 for the higher heating value of propane gas.
Lower heating value is about 10% below that. All those calculations that we've done on this are based on higher heating value and efficiency. I think Steve used an efficiency number of around 80% for propane. Did you use it at 80% yes. Or 100% for propane that's discharged into the building itself?
We used 100% for the direct fired equipment, 80% for the indirect.
Yeah, typically the lower heating value for propane is about 10% below the higher heating value, slightly higher than that. I think it's 9%, 8 or 9% below. The Europeans all love lower heating value because it makes biomass look more efficient against it's reality, I guess, because it doesn't produce water. It depends on whether you have condensing boilers or not. But in the U.S., I think everybody gets a little confused with the efficiency numbers from imported equipment and the fact that Europeans use lower heating value and the U.S. always uses the standard of higher heating value.
Well, great. I think we've covered the questions in the chat box, and I guess I would just like to kind of end the webinar here with a little, I guess, my own question here for Tom and Steve to address. But really, could you give us kind of in closing here, you know, what you see as the main benefits for moving to a wood heating system versus a traditional propane system, and also what you are seeing as some good recommendations for next steps based on the assessment you did here in Minnesota?
Kristen, one of the things I think that maybe is not being really studied well enough or looked at hard enough here is what are the advantages to really doing better environmental control in poultry barns? Is there a substantial gain to be made by really controlling humidity, nitrogen levels, or ammonia levels in barns, and being a little more precise? Can you lower morbidity? Can you lower mortality? Can you get higher hordes of animals going out and better conversion rates? My guess is you can. And what's a little ironic is that all this equipment, I know when I started, you know, they had these little remote hobos you could hook up and get lots of data, but they weren't able to control anything. And now for very little money, relatively speaking, there's all kinds of environmental controls that can give you a 4 to 20 milliamp signal that you can go ahead and control curtains or control fan speeds or control vents. I think there's probably the next step is that somebody's going to, one of these growers or integrator is going to figure out how to build a barn that's no more expensive than barns you're building today, but has a considerably better performance because they can control these environmental factors that are key to growth. And I think when that happens, you may see wood energy be significantly, or indirect systems be significantly more valuable. The next step I would recommend is, I think somebody at the university level or at the state level should fund a project where you put those pieces in place to try to capture those benefits if you really want to create that market for wood. You've got all these great pieces there. You've got the delivery system already in place. You've got farmers who aren't afraid to spend half an hour a day to either load a day bin with a loader they already have on site, or you know, check on their boiler and do the ash work or service it. You've got so well, if you could just find a little better boost on the payback or document what that better boost is, I think you could I think there's potential for wood energy to make an impact.
Great. Thank you, Tom. I appreciate that. I just put my contact information into the chat box. If anyone has further questions, please get in touch and I can facilitate getting any questions you have answered. I want to thank everybody for attending the webinar today, and especially thank our presenter, Steve, and panelist, Tom, with Wilson Engineering.